So as David mentioned, I'm a domain scientist, as you would say. So I'm a climate scientist, a physical oceanographer. And so I really come from the domain knowledge in a way, and really trying to use those tools to help or hope that we can advance science and what we can learn from data in general, and trying to push the boundaries of climate physics in general. So really, again, I'm here, I'm the one standing here, but the work is being done with a lot of people, in collaboration with a lot of people. Actually, some of them are in the room this evening, and so it's part of two big projects. The first one, M² Lines, which is supported by Schmidt Futures, really kind of accelerating scientific discovery with ML, with a big ocean focus, which is basically my area of research. Another one, the Science and Technology Center LEAP, which is led by Pierre Gentine, will be a speaker here actually in a couple of weeks' time as well. So let me get started and give you a little bit of a roadmap for what I'm going to try to cover. So I'm going to start with some challenges in climate science. As I mentioned, I'm a domain scientist. I'm excited about problem in climate from an ocean perspective, and really kind of trying to motivate a little bit what I think are the big challenges, what's exciting, what is it that we want to understand and why. And then, I put a question mark here, is it a new era for scientific discovery with AI? And so I'll give you a few philosophical points of what I think is happening and what might be happening in the future. Again, it will be my perspective, just to be clear, and kind of draw on some of the work that we've been doing in the last few years, again, in ocean and climate, how to put together physics and machine learning to help scientific discovery. And I'll give you a few concluding remarks at the end. Okay, so let's start with the open challenges. And again, as I mentioned, it's an oceanographer perspective, and it's my own. And I love starting with this quote and this image, which, the blue marble that you've seen from satellite imagery from Arthur Clarke. How inappropriate to call this planet Earth while it's quite clearly ocean, right? So basically, the ocean is covering 70% of the surface of the planet. So a pretty large body of water that is actually kind of a critical component of what we call the climate system, if you want. So, if we look at what's happening, so I think the pointer is here, here you go. So if we were thinking about scales, which is always useful, the ocean on average has a depth of about 4 kilometers, as opposed to the atmosphere, which is actually much taller. But if you think about the top 3 meters of the ocean, contains as much heat as the whole of the atmosphere. So a massive heat capacity. If you take the top 50 meters of the ocean, it contains as much carbon as the whole of the atmosphere. So again, a massive reservoir of heat and carbon that can actually store a lot of those important quantities that we know are critical for our planet. It can also move things around, right? So it takes up heat and carbon, but it can transport it over very large distances, so thousands of kilometers all around the planet. And so that's why the ocean is so important, very big reservoir of heat, carbon, and other tracer, and can move all of that around. But it's also very undersampled. So, in this era of big data, actually the amount of observations that we have are not as large as you might want. So there's still a lot of open questions on how the ocean works, how it might change in the future, and how it influences different parts of the climate system. So just to give you a little bit of a feel of what the ocean does, it actually takes up heat and carbon. So this is a little movie, a reconstruction of the past 150 years of heat uptake. So here what you see is when it's lighting up, that means the ocean has been taking up heat, and it's storing it at different depths of the ocean. And it's lighting up in different places, in the North Atlantic over there, or in the Southern Ocean. And those high latitude areas are a little bit of the lungs of the climate system, if you want. The ocean up there can actually absorb most of the heat and transport it at depth over great distances. So really, what's happening at the high latitudes are really a key component of how the ocean works and why so much heat and carbon can be taken up and moved around. And so it's just to give you a little bit of an idea of how much or how big and vast the ocean is and how important it is for the climate. So to continue with those open challenges, right? So how much heat the ocean has been taking up is one. How does that contribute to sea level is another important contributor. So if we look at the past 100 and so years, we know that sea level has been rising, and we've been observing it. And we can actually understand the different components. So part of it is due to melting of land ice and groundwater. Part of it is due to the ocean warming, so that means basically the water expands as it warms and sea level goes up. And so understanding those balances are pretty critical, again, to understand how the system is changing, but also how it might change in the future. And so this remains some of those open challenges of which component of the climate system are contributing to sea level, how fast that might change, and what will be the consequences. Other important open challenges are how different components interact with one another. We have the ocean, we have the atmosphere, we have the land. When the climate actually responds both to its own internal clock, its own internal variability, it will affect other parts of the climate system at great distances. If we change the external forcing, this will also affect the variability of the system, which will have an impact, again, on other regions. So those, what you would call teleconnection or complex interaction across different components of the climate system are still challenging overall for us to understand. So a lot of open questions in this area. And finally, sea level at the local level rather than at the global scale. Right? So again, here's a picture from Manhattan flooding in 2021, I believe, in this case. So this is something we experience, right? New York is not the only place. Understanding where this flooding is coming from. Is it because sea level has been going up just by itself, so it's actually now more likely that flooding can happen? Is it because the storms are stronger? Are we seeing more extremes? So actually being able to both quantify the extremes and understanding their drivers are all open questions. And just from a scientific perspective, not just as humans who actually experience those changes in climate, there's a lot of exciting science, right? We're basically trying to understand a system that is very complex, highly nonlinear, very turbulent and chaotic, non-stationary. That means its statistics are changing all the time. So this is not something that you can easily quantify. And it's multiscale and multiphysics, right? So basically we're thinking about thermodynamics, dynamics, across the ocean, atmosphere, macrophysics, pretty much you name every single component that you've learned in physics at some point or another, and it's going to be part of the climate system. So again, as a domain scientist, it's actually a very exciting area to work in because there's a lot of physics and science to be done and to be understood. So I come from this kind of multi-scale, field, if you want, and focusing on what the ocean looks like or the scales of the ocean. So as I mentioned up there, the climate system has many components, and so we're only going to focus on the ocean here. So what we have is we usually have wind and buoyancy, so basically heating and cooling, that are driving the large-scale ocean circulation. So you can have transport all over the planet, and it's very efficient. And we have pretty good theories for that. Now, how this transport changes gets a little bit interesting and exciting. So we have instabilities that get developed, again, because we have a turbulent fluids, and those instabilities start basically cropping up at different scales. So this scale here of 10 to 100 kilometers, we call them mesoscale, and they're quite important. They depend actually on the rotation rate and how the ocean density is set up. So as a function of depth. So their scale is very much determined by this kind of balance between rotation and, again, what we call stratification. Those instabilities can, again, kick off different type of instabilities. Some of them are derived from the larger scale. Some of them are forced by other components of the climate system, all the way down to meter scale. So we really have thousands of kilometers all the way down to meter scale where you have dissipation and mixing overall. So you can think about this, right? So you want to understand the climate system. You need to understand this entire range of interaction because those small scale actually feed into the large scale. So it's not that one scale by itself is enough. If you want to understand the climate system, you really need to understand this full spectrum of scales and how they interact with one another, from meter all the way to thousands of kilometers. So a true multi-physics, multi-scale problem. Now, the good news, you could say, well, we have equations for it, right? We have Navier-Stokes overall. So, if you're familiar, it's, basically Newton's law, all right? And it's partial differential equations. Again, they are complicated. The issue is we don't really know how to solve them, right? So we have laws, but we don't know how to solve them. They describe a lot of the physics, but again, solutions are, still, to be found in a way. We also have components of the climate system like the heat equation, the salt equation, the equation of state that relates density, temperature, salt, and pressure in the ocean. Those are empirical, actually. So they have some components that are just, fitting to some data sets. So we have some knowns that we can solve, and we have a lot of unknowns that we haven't observed very well, for which we only have a few data points or a few empirical laws for it. So you can see where I'm going there, right? A lot to discover and a lot to understand. So what I call scientific discovery then, right? So if you think, Newton, you start with some data, which is usually a little bit of, a couple of measurements or something like this. You have an empirical relationship that will actually describe the data set that you have. Then you try to come up with a theory, which, again, you can think about it as a robust interpretation of the phenomenon that you're going after, right? It can be gravitational attraction, or you can think of different type of problem. And then, of course, you try to actually build an experiment to make sure that your theory really works in the way you developed it, and also based on more data if you do. Now, what's scientific discovery now? So you could think in this age of machine learning and data, well, it's not that different in a way, right? So I still have data, but rather than have a few measurements, now I have high-dimensional data, right? So I have a lot of it. I have a lot of information. But I still fit to some empirical function, all right? So any machine learning algorithm that you come up will try to do that fitting for you. So rather than you scratching your head, then you can ask the algorithm. But, again, as domain scientists, that's not enough, right? We don't just want to get a good prediction. We want to understand something that will work across scale. So we're still trying to bring our domain knowledge into the picture and build a theory that is robust enough across the phenomenon that we care about. And then, rather than going to the lab, usually we actually run a simulator, right? So hopefully, if we get the right theory, then we can use computers to help us test that theory and make sure that whatever we developed is actually, again, robust and can generalize to all the conditions that we care about. So, the question is, do we have a paradigm shift now in the age of AI? Or is it just the natural evolution of moving from little data to big data? And we still continue to use domain knowledge, theory, computing, but with a slightly different flavor to it. And so that's the way I think about this, and I think about it as blurring the boundaries across disciplines. So, again, you can think about data versus theory. I like to think about this as actually blurring the boundaries. And so, whether you have AI or data at the center versus your domain knowledge, I don't see that as being separated. Actually, I think we are in this era where everything matters. Data is there for us to use. We've been using computers for a very, very long time, and we will continue to use them. And domain knowledge remains central for us to actually push our understanding and asking the right questions. So this new era, for me, is really a natural evolution of where science has been and will continue to be. It is driven by scientific curiosity. We're going to use all the data that we have. We continue to push theory and simulations together to actually bridge that gap. So I really see data and computing as continuing to be embedded in this endeavor of scientific discovery. So I told you I will give you a little bit of my philosophical perspective on how to use AI in the sciences. So now, what's the potential for AI for scientific discovery? So I've got those three possibilities: smarter, better, faster, and different. Right? So I'm going to try to argue those four are useful for actually pushing the boundaries. So smarter, all right, so everything is in quote here, obviously. So smarter, it's just accelerating discovery, right? So now we do have a lot of data, and we need to sift through it. So can we extract knowledge in a way that is efficient from that big data and actually probe our understanding of the big question? And again, for me, it's multiscale, multiphysics, and the climate problem. So that's what I mean by smarter. Not necessarily smarter than us, but actually can help us sift through all that data. Again, in this case, it will be simulation, to try to explain this multiscale physics. Better. Well, the hope is, if you sift through all of that data and you can get better, physics representation in your simulators, well, that means you can hopefully improve climate models, for example, or any models for which you can't resolve all the scales that you care about. So that will be the better, right? So you improve on whatever you had before. Faster. Well, the good news with AI works really well on GPU, so you can actually run simulators really, really quickly. So can we actually emulate say, the climate system overall, just based on data, and run those simulators really quickly. They might not be perfect, but what I like about science is I like to have test cases where I can falsify my hypothesis. So if you can run those simulators, and you can run a lot of them, it's not necessarily that you will end up with the best simulator ever, but you will be able to actually test your hypothesis a lot faster than before, because we still have limited computing. And different. So what do I mean by different? Well, it's always good to actually, think a little bit differently about problems and see where you land. So kind of kicking things around a little bit and trying to rethink our old assumptions in a way that quite often, we've been using it for a very long time, and so always good to actually think a little bit differently. So it's really kind of this integrated thinking where theory, simulation, data, AI are all embedded within this kind of range. And so that's what I'm going to try to kind of, demonstrate now with a few examples. So I'm going to pick some example for motion, as mentioned, and I'm going to start with the first one. So, the smarter part. Can AI actually help and improve on our knowledge when it comes to climate physics and ocean physics? So the first question is, can we develop theory for physical processes and their interaction across scale, right? So I'm going back to this kind of picture where I know that I have, large-scale forcing driving those currents. I have some instabilities being derived all the way down to the meter scale. Some of it I understand, some I don't. So is it possible for us to actually learn something from data that will teach me how those physical processes respond to forcing, how should I model them, how should I think about them? The second question is, when I actually learn that new physics, can I use it, right? Can I use it in a meaningful way? And again, I'm a climate physicist, and I like to, model things, and I like to use climate models to understand how the climate system might change in the future. So can I use that new physics and integrate it in a real climate model and hope that my climate simulator will be better, right? So there are a lot of physical processes in climate models today that are not resolved. So basically, any mixing process that is happening below a scale of about 50 kilometers, so basically everything you have on the right-hand side here is actually not resolved in a climate model. It's being parametrized, as we say. So we basically come up with an empirical fit that will describe the relationship of this mixing with turbulence on the large scale. And so again, usually the theories, we're relying on a small amount of data. So now the question is, can we replace that with something that is learned directly from data? So, well, should ask ChatGPT. How do I use machine learning to improve climate model? That's what we're going after, right? So if ChatGPT says something, I should follow it. So ChatGPT says, one way to use machine learning is to actually emulate the subgrid processes. So that's all the small scale mixing that we have in the ocean that we don't resolve, and that we should do that, using machine learning in a way, it says neural network somewhere in there. So it's exciting, ChatGPT basically gives me the vision of two of our projects. Obviously, I tapped that long after we were funded, so probably used some of our website, but nonetheless, I felt pretty pleased about this, let's be perfectly honest. All right, so that's gonna be the story. Now I'm gonna tell you the truth, how we really do it. So it looks like this. So we're gonna take some simulations. Again, I wanna make that clear, I'm not gonna use direct observations. We're still gonna simulate with what we're gonna call high fidelity simulation, for which, again, we can resolve the processes that we care about. So we're going to generate a wealth of data. We're going to use machine learning algorithm for the main part. Again, they will be constrained by some physics in some cases, and sometimes we let it be free. And what we're going to do is we're going to try to learn the physics that is missing from coarse resolution climate models. Okay? So everything that is happening that is too small to be resolved by the grid box size of my climate simulators, because I'm constrained by compute, right? And I'm gonna show you a few examples of that. So the climate simulators are run at a relatively coarse resolution, and we're gonna add a term that we're gonna integrate with that will represent the effect of, say, mixing on the large scale temperature, and so on and so forth. So interestingly, in the atmosphere, those ideas came about in the late 1990s, which is kind of remarkable in a way, using machine learning and neural network to try to emulate part of the atmosphere. And then nothing happened. One paper came about, and again, nothing happened. And then my colleague Pierre Gentil and a few other groups started reviving some of that. And again, Pierre will talk about what's happening in the atmospheric side in a couple of weeks. Exactly at the same time as the paper on convection in the atmosphere, we were working on ocean turbulence and also showed the promise of using data and machine learning to represent different type of turbulence in the ocean and improve climate models. And so that's what we're going to look at. As I said at the start, and I think it bears repeating, this is really work that is done very collaboratively across multiple institutions in the US and France, again, with a lot of very talented scientists that do pretty amazing job. And I think it's part of the philosophy here is bringing machine learning experts, domain scientists, computational scientists all together to work on a big problem over a sustained amount of time. And I think that's why it's so exciting. Okay, so before we go into a few more results, just a final word of kind of high-level picture and semi-philosophy. So in general, we can think about error versus complexity, which will be complexity will be the number of parameters that we have. So if you have very few parameters in a function that you try to learn, it's very likely that the error will be large. And that's exactly what we find when we use some of the empirical fitting for how to represent mixing in general. Right? So usually you come up with a functional form. You can think about diffusivity, and you'll have a coefficient over there. So it's very simple, right? Degrees of freedom, you can think about 1, just the viscosity or the diffusion parameter. And it's a little bit limited in a way and doesn't really represent how mixing works. That means that the error will be relatively large because your complexity is low. But interpretability will be great, right? Because I know exactly what that function looks like, and I can give you a whole story about this. Now, if I go to the other side, I increase the number of parameters, all right? So that will be your neural network. You can have a bazillion number of parameters, and you can feed high-dimensional data and high-dimensional statistics to learn the best representation of physics possible. So now the good news is the error will likely go down because you have more parameters, you can fit more complex data, but interpretability will go down. Very hard to actually interpret what's going on under the hood of your neural network, given the amount of complexity and the large number of degrees of freedom. So I'm going to show you a little bit of everything. We settle with some ideas that sit over here, which is still extracting information from data without any a priori assumption and trying to learn equations from the data. So that's going to be a little bit of our trade-off. We're going to sit somewhere here in between. Interpretability will be easier because we're going to have less degrees of freedom, but we're not forcing our assumption to sit over here. So we're not going to have, some assumption about what a functional form should look like, but we're going to try to not end up all the way there where it's way too complicated for us to actually make scientific advances. Okay, so I'm going to show a few examples now. And the first one is what we call boundary layer mixing. So this is a schematic of the ocean. So this is depth. And again, what's happening in the boundary layer is you basically have wind forcing at the top. You have a lot of buoyancy, and things are mixing overall, right? So if I were looking at the profile of density as a function of depth, so the density in the top layer is basically constant because you mixed so well through the forcing, through the turbulence, that you have basically a uniform vertical temperature. Okay? And so that's what we're trying to represent. How the forcing generate this mixing in the top layer of the ocean and trying to learn a good representation of it from data. Okay? So now you can always start with physics because physics is pretty good, right? So we know that vertical mixing in general, again, those are all theories, can be a diffusivity time the gradient of the tracer that you care about. So I can mix that and it's a pretty good theory. Using dimensional argument, the diffusivity will be a length time of velocity. Again, that's a pretty good way to think about it, right? So I can mix over a given length scale, okay, with a certain velocity, because this is a turbulent process. So you can think about faster velocity, your mixing rate is actually going up over a certain distance. So very basic physics 101. Now, how do you write this diffusivity? Usually you can't quite measure it. So now you need to start decomposing it a little bit more. And so the diffusivity will depend on, the depth of the layer that fills the mixing. So that will be this H over here. And the good news is this H can be constrained by some energetics. So that's good, we have a theory for it, okay? So we start with some theory and some approximation, we continue with a little bit of a theory, and then there are two additional pieces. One is the vertical profile, basically kind of a structure over which you actually do the mixing. So this is completely ad hoc. It goes back to a paper in the 70s, which is called a universal function. This very little universal. It's based on very little data and a rather ad hoc function that everybody has been using for 50 years. And an additional velocity scale that has, a little bit of a scaling, but does not really depend on the forcing. So we have two pieces of this representation of vertical mixing that are quite ad hoc, and one that is well constrained by physics. So can we use data? So can we run simulations that actually mimic, or represent very well this turbulent mixing, and learn those two pieces that are ad hoc, right? So we keep everything that we like, that is physics-based, and we learn the pieces that we think are still not well, or not describing, the physics of the process that we care about very well. And so we learned that, with machine learning and neural network. And so this is work led by Akash Sane in Princeton GFDL. So only learning the pieces of the physics from data that we don't necessarily trust. Now, if you do that with a neural network, what you hope is you can extract some information out of it, okay? So as I mentioned, neural networks are great, but hard to actually interpret. So what Akash has been doing is trying to actually find an interpretable representation of the neural network. And you can distill that with methods like equation discovery. So you actually try to learn an equation from the output of the neural network that you have by finding good relationship between the input and output of the functional form that you're looking for. There are always pros and cons, so I'm not going to give you only the stories of everything works, right? So actually those algorithms are non-trivial to actually get to converge. They can find relationships that are hard to understand. So right now, what's being found here is actually a new relationship that is different than the original one. Seems to work well, but nonetheless, there's still a question mark on how physical and how generalizable it is. So we're only at the beginning of those advances, but this is kind of opening the door of learning physics, or at least something that is interpretable, that can improve upon the old theories and can generalize as well. So that was the smarter question mark, right? So we potentially learn new physics that is generalizable across a wide range of wind forcing, buoyancy forcing, again, something we didn't have before. Now the question is, if I use that in a climate model, am I improving the climate model, or am I doing even more damage than before? So this is the error between the climate model and observations with the old representation of mixing, okay? So that's kind of the original error. So basically, if it's not white, that means there is an error. Just think about it this way, okay? So there are a lot of errors, and this is the error on the depth of the mixing in the climate model. And it's average over several decades, right? So this is a statistics, if you want. So now if we were replacing some of the pieces with the neural network, so what you want is to have more white, right? So we want to kind of reduce the problem. So here's where we are. So we have more white. So in some places, we actually improve the climate model by replacing some of the pieces with neural network. But in some places, we do worse, right? So you might fix a problem, but you might create a few others. Now, what happens if we use the equation discovery instead? So is that better or worse? So it's a little bit in between. It does better than the original parameterization. So again, you see, it's a little more white than this one, but it's not as white as the one in the middle. So the equation that has less parameter help, but nonetheless is not as good as this kind of high-dimensional representation of the physics. So this is a way for us to actually try to push ourselves in a way, what is missing from those low representation of the physics that is not characterized, and what is it that the neural network with this kind of high-dimensional space has captured that we're still missing. And so I told you I'm not going to give you only good stories, right? Still a lot of open question, but this is kind of pushing us to do more than kind of the traditional approach with low data and an old theory and trying to push us to actually understand what's coming next. So the second example is what we call ocean mesoscale eddies, right? So those 10 to 100 kilometers in scale. So what we have here is a simulation of a climate model run at three different resolutions: 100 kilometer, 40 kilometer, 10 kilometer. And you're looking at the surface temperature in that simulator. And hopefully you can see the difference. This looks like peanut butter, right? It's very viscous, all the way to something that is very turbulent. Okay, so we're looking along the Antarctic Peninsula here, and you can see really as you increase the resolution of the climate model, you actually increase the amount of turbulence, which makes sense. And the question is not how to make this model look more turbulent, because I can't do it unless I increase the grid box size, but how to make the physics of this model as good as the physics of this model without increasing computational cost. So what we want to represent is the effect of those turbulent eddies, which are actually quite important in the way we take up heat and carbon in the ocean. So trying to capture their effect on the large-scale temperature. And thereby, hopefully, improve this low-resolution climate model. Okay, so again, we're back to learning from data. So we're going to take high-resolution data, and we're going to try to learn a mathematical representation for this turbulence, okay? So here we're going to directly learn from data. We're not going to go through the machine learning, neural network, and so on. We're directly going to try to learn equations from some high-resolution simulation. And so again, it's just, I'm not going to explain what's going on there, but we have a couple of methods. One, which is what we call genetic programming. You basically add, multiply different functions through the data, and it spits something out. Another method is you give the algorithm a set of library of functions, so derivatives and so on and so forth, and it's going to prune through that library of function. In either case, we end up with the same answer, a nice tensor that you can go and actually analyze after the fact. So rather than a priori deciding what the function should look like, how the turbulence impact the large scale, we actually learn that directly from data. And so this is kind of a different way, again, to approach the problem, where you learn an equation directly from data and trying to understand how momentum, energy is actually exchanged as a function of scale. So kind of going back again to this multi-scale problem for which those turbulent features affect the large-scale flow. So here we do think we've learned something. So I removed the question mark of smarter. So it helped us actually find different terms that we didn't anticipate before in how this kind of turbulence works across scale. Now again, the question, is it better? So now the question marks come up. So now we're going to take this kind of new representation of eddies, put that into a climate model. So now we know we extracted some knowledge. We implement that in a global climate model, and then we see if we again reduce the error. So up here, we're looking at the temperature error in the model relative to observation. So where it's red, that means the model is too warm compared to the observations. Where it's blue, that means the model is too cold relative to observations. And this is one model, but actually if you take any climate model that there is, you'll end up with the same error. And this error has been around for several decades. So it's called, the cold spots. There are many names for it, but it's basically the Gulf Stream, so the strong current that detaches from the US East Coast, usually at the wrong place, and does not transport enough heat to the high latitude. So that means there's too much heat accumulation along the North Atlantic, along the US East Coast, and basically a cold anomaly away from it because we didn't transport enough heat compared to the Alps. So now if we take our new representation, new in quote again, representation of that turbulence, and integrate our model with this new representation, what we're trying to do is to reduce that error, hopefully, if it works. So it does, but I'll tell you also the bad part. So right now, just to make clear, what we're looking at is the response when we include this term, not the response itself. So not the net error itself. So that means when we plug in our parameterization, we basically end up with a negative response here. So I need to sum those two to get the real answer. So where it was very warm, I'm adding a perturbation that is negative, so I bring it back closer to the observation, so that's good, right? So I'm reducing the error. Every time I have two different signs, that's good. And where it was too cold, now I'm making it warmer. So again, I bring it closer to the observation. So in this case, again, it's good news, it worked. But if you look at different regions, actually we make other places way worse. So the Southern Ocean, for example, which is another place where we care about, the error got worse. And it's always hard to figure out what's the reason. Is it because of our new physics, or is it because something else is compensating for the error, other pieces of the physics we didn't learn? So we are moving towards improving climate models, but also we actually like to bring people in. So this is a visualization of those new simulations that we're running with basically data-driven, representation of physics, and we're putting the data out there, mostly for people to, analyze the data set, and not just, telling us what we're doing wrong, but also where the issues are. So really trying to actually give the data to people so we can actually work together and analyze those data sets. We really are trying to make, this kind of idea of representing, model, data, physics together really as open as possible. And so it's a collaboration, again, between LEAP and M² lines, and really something that we're keen in, engaging with the community. So anybody can access this data set and play with it. So we have notebooks that anyone can use. So I give you a few challenges, but there are many more, right? So I'm using data that is imperfect, that come from simulations. I'm still learning representation that are approximation. They are not truth. They're not, they're not fundamental laws at the end of the day. So, whether it's, uncertainty quantification that is missing, that I haven't talked about. So for, any prediction, this is completely missing. When we implement those, new representation, the models quite often go unstable. So there's a lot of work going on behind the scene to actually make that work, and so on and so forth, right? So I can list hundreds of challenges. Of course, we work on a lot of that. And again, people in the room are working on this. So generative AI, right? So the same technology that we use for ChatGPT can help with uncertainty quantification and kind of learning probabilities along the way. Embedding symmetries and invariants within, the machine learning to make sure that we respect some of the physical laws. So all of that is still, in progress and still a lot of work to do. Again, Pierre, Gentil, in a couple of weeks, we'll talk about what's going on in the atmosphere and clouds, but the same principle, trying to learn equations directly from it. So we talked about smarter, so learning equation from data and trying to learn new scale interaction. We talked about better, so using this potentially new physics learned from data to improve climate models. Now I want to talk about faster. What if you run your climate model, and again, you're not a climate modeling center, or you have your own simulation of plasma or astro or whatever, but it's too big for you to run on a computer, but you still want to run a lot of simulations. So if somebody actually run that simulator for you and gives you the data, can you emulate it? So basically, can you emulate the full partial differential equations from the data itself? So I'm sure you've heard of, several of the paper in weather forecast, which can actually beat to some extent numerical weather prediction given the initial condition over a certain number of days. So what we're trying to push here is to actually run climate simulators, meaning decades, or years to decades, using data coming out of the modeling centers. So this is work that is led by Adam Suba, who is a PhD student at NYU. So we're taking data from this big, complicated, coupled climate model. Data is saved, and so what we're going to try to do is to actually learn the simulation given a basically short time steps, okay? So now we're not learning the missing physics, we're basically learning the full evolution of the PDE over a short amount of time. So this is a movie of the temperature at the surface in one area of the model. So right now we're doing it per region. So that's going to be the truth over here. So this is the real coupled climate model, simulated, sorry. And those are going to be two different machine learning algorithms that have learned from the data over a short time scale and basically going to be run for several years, okay? And what they're going to see are going to be some initial condition and some surface forcing. And so let me play the movie. So this is the truth. And this is what we learn from data and actually run for several years. It's actually pretty remarkable, in all honesty, right? So, of course, it depends a lot on how you do it. And how you do it, what's important is the type of forcing that you apply and how you actually separate slow and fast timescale. But that means that now we actually are moving towards emulating years, if not decades, of climate simulations with machine learning. After you trained it, it actually runs in minutes or seconds as opposed to months on supercomputing from the Climate Modeling Center. So the faster here is not so much about having a perfect simulation. It means that if you want to falsify your hypothesis and try a few things out, now you have this kind of emulation of your climate model that you can go and try, and anyone can do it. And so I think this is a very powerful way to use machine learning, not just to improve the simulations or to learn something from data, but also to have this way to falsify our hypothesis and again push scientific discovery in a way that is useful. So, I mean, again, I'm not going to go into the detail because there are too many curves, but the black line here, the dashed black line, is the temperature as a function of years from the climate model. And those are different emulators. So in some cases, the emulators are terrible, right? And we learn from that. We actually learn what was needed to make them good, to make them stable, and to run them for a large amount of time. And the story is always the same, domain knowledge. Setting the problem as a physics problem is usually the way to actually push those emulators to work well. And so just to give you something, by the way, those movies are actually from last night. So Adam submitted a paper literally yesterday. So this is brand new. So this is we're pretty excited, let's be honest. Still a lot of work to do. We're still contained on the regional scale, but a very exciting way forward. So smarter, better, faster, and then different, all right? So that's gonna be our last one. So different. Right now, we've used data coming out of simulators directly, and we use them as truth. I've never used observations anywhere, right, so far. And one of the reasons is probably my first slide. I told you the ocean is kind of poorly sampled. So for the problem that we have in hand, it's probably going to be difficult for us to learn everything from data from scratch. So what we're trying to do is something a little bit brute force. And so this is led by Will Gregory at Princeton JFDL. And he's going to learn the error between the model and the observations, okay? From something that is called data assimilation, which is, again, a great way to merge simulation and data and trying to get the best representation, the best historical representation. And he's been doing that for sea ice. So what do I mean by that? So this is sea ice concentration in a model. So the blue line is actually the model itself. And what you see is that the model is drifting, right? It's basically moving away. The crosses are the observations. So if you start your model, it's moving very far away from the observation. And so what you try to do is to push the model towards the observation. And that's what data assimilation is doing. Kind of in a rough way, you basically take a weighted average of the observations and the model given some uncertainty. And I'm exaggerating in the way I represent it, but that's kind of the baseline. Now, what the data assimilation does is, in general, it actually tries to push the model towards the observation in the same direction, meaning that the model is drifting in a systematic way. It has its own climate that pushes it, again, away from the obs, so that's not good. And what we're trying to do is to learn that correction. We are missing some physics. That's why the model is moving away from the real observations. So can we learn that? Can we machine learn that? And actually use it when you have no observations at all. So this is an indirect way to learn the missing physics from the simulators by embedding some observations, but again, in a slightly convoluted way. Good news, it actually works, which is, I'm still blown away by it. So this is going to be the error in the model itself, all right, that has no, it's basically left alone, and the difference between the model and the observations. This is when you add a machine learned correction, and this is easier to look here. So this is going to be the error as a function of time. So when the error is high, right, so that means the model is drifting away. And the blue curve is when we add this correction over years for which the data wasn't seen. So it's actually learning correction over a certain time scale and applying it on years for which it's never seen the data at all. So again, we're still kind of, amazed that it's working, we just don't know why. We don't know what we learned. We know we learned something, and we know it works even when there is no data, but we haven't understood yet what's the state dependence that we learn. And so again, is it smarter? What are we correcting for? And this is exciting again because it pushes us to actually figure out what was missing in the sea ice model or in the ocean model that we can capture in this way but couldn't otherwise. So I'm getting to the end, so I want to come back to this point here. I don't know if we're in a new era. I see that as a continuation of where we've been, using data, some empirical fit, however you want to talk about it, to push our theory with simulations and really try to answer big questions in climate physics through this kind of, combination or, blurry boundaries across different disciplines. And I see that only as the beginning. I really don't see that as the end. Really pushes us to think very differently, but also, make sure that we ask the right questions overall. So again, a lot of work is going on with a lot of people. They really are doing all the amazing work, as I mentioned, but a lot of that is open source as well. So anybody can grab our code, the data, anything you want, and get in touch. There's a lot going on across the board. So let me say a few things. So our goal at the end of the day, or at least my personal goal, right, is still to try to build strong foundation and understanding to advance key processes or key questions in climate science. This is what motivates me. This is what I'm excited about, right? So whether it's heat and carbon uptake, sea level extreme, how to attribute climate change, this is usually what, gets me excited. I think, there's a lot of physics there that we don't understand. I think we can improve and accelerate climate model development overall. I think AI is, a good way to do that. We can replace, some ad hoc representation of physics and, try to improve on our knowledge, but we can also try to emulate it faster. So now again, this technology helps us accelerate how we do scientific discovery or push us forward. I still, kind of reiterate the point that data and computing are embedded in scientific discovery. They've always been there. Now we just have more of it. So we need to think hard on how to use it and to make the best use of it. But I really think it's one way to bridge the gap between, theory and simulation. AI has been very much at the forefront of it. I think it really, again, I think it's only the beginning. I have no idea what comes next, in all honesty, but I'm definitely excited. And a lot of fields, are also moving in this direction. Climate is just one of them, right? And so I surely can't wait to see what comes next. And I think, boom, bang on. It's my 10 minutes. Thank you very much.